Today we're going to be looking at the review stations. I strongly recommend that you actually do the review stations. You can find them as a PDF in the Algebra Basics folder before you watch this video. Go do the stations before you watch this video. Now, what are stations? Well, in an in-person modality, I would reset all the desks in the classroom into little pods, and I'd put a station at each pod, and you would go from station to station doing the various problems at each station as an active review for your assessment. Well, we're not getting together in that way, so I thought for your first stations that I would make a video of them. This first station is all about simplifying exponential expressions. And let's start. We've got 14 stations to get through. Station number 1, problem 1, looks like this. Negative 64x to the third over z to the sixth, y to the ninth, raised to the 2/3 power. And the first thing I want to do, since I don't see any pluses or minuses here, I can apply this exponent to all 4 of these objects. And when I do that, my problem now looks like negative 64 to the 2/3 and x to the third to the 2/3 and z to the sixth to the 2/3 and finally y to the ninth to the 2/3. And what's our rule when we raise a power to a power? When we raise a power to a power, we're supposed to multiply those. So 9 times 2/3 is going to be 6. So now on the bottom, I'm going to have y to the sixth. When I raise a power to a power, I know I'm supposed to multiply them. So 6 times 2/3, these will cancel, leaving me at 2. And I get z to the fourth. Now what about here? X to the third to the 2/3, that's going to be x squared when you cancel out those 3's. And now here with the negative 64. Remember, negative 64 is, negative 64 is actually negative 4 to the third power, raised to the 2/3. So these are going to cancel, and then I'm going to have negative 4 to the second power, which is going to be what? Positive 16. All right. So, but I did need to recognize that negative 64 was negative 4 to the third. And we talked in, I think it was the first video for this Algebra Basics unit about doing problems like that. So you might want to go back and review those things. Okay. Number 2. Number 2 says x y to the negative 1 over square root of z to the fourth times x to the 1/3 y squared over z to the 3/2 cubed. Okay. Even before I apply this exponent, because I don't see any pluses or minuses, I can do that. I'm going to think about this. So square root of z, remember, is the same as z to the 1/2. And I think I'm going to change this right now. Like my very first step would be to rewrite that radical with a rational exponent. Because now I'm going to be applying the power on the outside to each of these things, and I can do that in both cases. And so I'm going to have x to the fourth, y to the negative 4 over z to the second times 1/3 times 3 is 3/3 or 1. And then I'm going to have y to the sixth power. Yeah. And on the bottom, 3/2 times 3 is going to be z to the 9/2. Okay, so we're multiplying. The bases are the same. What can I do with these exponents? That's right. When we're multiplying and the bases are the same, we add the exponents. So this is going to now be x to the fifth. Negative 4 plus 6 is positive 2. And now I've got z to the second times z to the 7/2. And because I'm multiplying and the bases are the same, I'm supposed to add them. But this has a denominator of 2, and this doesn't, so I better make a common denominator. And so that's going to be 4 plus 7, or z to the 11 halves power. And that's going to be my answer. Okay? Z to the 11 halves. Z to the... Oh, was that 9? That's 9. That is 9. That's a 9, not a 3. I'm not a 7. That's a 9. So 9 plus 4 is 13. Oops, that one's still 9 halves, 4 halves, and here 13 halves. Okay, sorry. That was a hard to read miss, and I read it wrong. Okay, problem number 3. On this one will be a to the 2/3 times b to the negative 2 raised to the 3rd raised to the negative 1. Now, I know some students like to apply this there first, and then they apply the negative 1. I like just to take care of those. When I raise a power to a power, I multiply those powers. So now I'm looking at a to the 2/3 b to the negative 2 raised to the negative 3 power. And I can apply that negative 3 to each of these. 2/3 times negative 3 is going to give me a to the negative 2, and negative 2 times negative 3 is going to give me b to the positive 6. Now, you can leave your answer like that if it doesn't say no negative exponents, or if it does say no negative exponents, I'm probably going to move that a stuff onto the bottom and turn it into positive. Okay? So there's our first station. And let's now move on to the next one because we've got 13 more to go. All right, station 2. Station 2 looks like it's all about working with radicals. And so let's remind ourselves about working with radicals on station 2. So the first problem, x minus root 3, x plus root 3. Well, ideally, I recognize that this is a difference of squares, and a difference of squares always spoils to be this one squared minus this one squared. And so if I know that pattern, I can just write x squared minus 3. If I don't know that pattern, then I have to FOIL. So I'm going to have x times x. I'm going to have plus x root 3, and then here's minus x root 3. And then negative times positive is negative. Root 3 times root 3 is root 9. And what is the square root of 9? Well, the square root of 9 is 3. And what happens to these middle terms? You've got a plus x root 3 and a minus x root 3. That's right, they cancel each other out. So I end up with that same x squared minus 3. So I didn't actually have to know the pattern. Knowing the pattern, though, would have saved me some time. Okay, problem number 2. This time we're asked to distribute root 3 to root 27 minus root 12. Now, a word about this. There's 2 ways I think about doing this. One is to do the distributing and then simplify. The other is to simplify these radicals and see if we can do the subtraction first. Maybe we should look at both methods. Okay, my experience is that students like to do the distributing. So 3 times 7 is 81, minus sign, and then 3 times 12 is 36. Well, that's nice. That's going to be 9 minus 6, 4, 3. That was pretty painless. What if instead of taking that approach, I had actually tried to simplify these first? Well, 27 is 3 times 3 times 3, and it's a square root, so I can pull out a 3, 3 root 3. And 12 is 2 times 2 times 3, so I can pull out a 2, 2 root 3. And look, these have the same radicand. So I can actually combine these like terms. I can do the subtraction. 3 of these things minus 2 of these things is just going to be 1 of these things times that one out in front. And then root 3 times root 3 is root 9, which is 3. So I can get 3 either way. Yeah, so you've got 2 different ways to think about doing that, to simplifying that expression. And I don't particularly care which one you use. I recommend whichever one you're more comfortable with. Problem 3 asks us to consider a cube root of 8x to the 5th y to the third, z to the fourth. Now, some people are comfortable looking at this and saying, oh, I know what comes out. A 2, an x, a y, and a z, and the 3, x squared z is left over. But there are a lot of students who can't just do that. So let me show you, if you're in that latter category, this is how you might want to do this problem. You've got a cube root. 8 is 2 times 2 times 2, x to the fifth times y to the third times z to the fourth. And I know because this is a cube root, I can take out 1 from each group of 3 that I have. Okay, so what am I taking out? A 2, an x, a y, and a z. Who's left over in this cube root? Well, I took out all of them, I took out all of them. Oh, I still have this x times x. And I took out all of that, I took out all of that, and I still have a z. And so I would write x squared z here. Okay? Now, how did I do it so fast? Well, I said cube root, and so 3 goes into 5 once with 2 left over. And I said 3 goes into 3 once with none left over. And I said 3 goes into 4 once with 1 left over. So yeah, I can take care of this that way as well. Okay, there's problem 3. What about problem 4? Problem 4, we're asked to do some rationalizing. Here we're rationalizing the denominator. And so for number 4, we have 3 plus root x over 3 minus root x. And I remember from our second day in this unit when we were talking about radicals and talking about rationalizing denominators, we said we would need to use what? What was that C word? 3 plus root x is the conjugate of this. And I have to multiply top and bottom by that conjugate. Why don't you pause the video and try that right now, if you haven't, and see what you get. Okay, so welcome back. I'm going to have 3 times 3, which is 9. I'm going to have 3 root x plus 3 more root x, which is 6 root x. And I'm going to have root x times root x, which is x. Actually, it's absolute value of x, but we're going to be fine with that. X in our class. Okay. What about the denominator? Well, that's a difference of squares. That's what happens whenever I use the conjugate. And as a result, I know my answer, or what I get when I'm done FOILing, is simply going to be the first one squared minus the second one squared. Okay, now you can't cancel those. If these things were all attached by multiplication, then sure, you could cancel. But see the pluses and minuses? That makes this you can't cancel, or I come after you with the pool noodle. Okay? No pool noodle for you. Please do the foiling if you're not sure. So that was station 2. Let's take a look at station 3. Station 3 seems to be about polynomials. We're subtracting 2 polynomials, and then we've got a lot of multiplying of polynomials. Okay, let's see what this first one looks like. Station 3, and problem number 1 says 3x to the third minus 4x squared plus x minus 7 minus x to the fourth minus 2x to the third plus 3x squared plus 5. Well, actually, the first thing I want to do is I want to apply that negative to each of these things. So I'm going to have 3x to the third minus 4x squared plus x minus 7 minus x to the fourth. Minus times minus is plus 2x to the third. Minus times plus is minus 3x squared. And minus times plus is minus 5. That is a 5, right? Yes. Okay, so now combining like terms. Well, I only see one x to the fourth, so we have negative x to the fourth. That takes that one. I've got an x to the third and some more x to the third. 3 of them plus 2 of them is going to give me 5 of those x to the thirds. Now they're gone. Minus 3x squared minus 4x squared is minus 7x squared. I've got a plus x. And then minus 7 minus 5 is minus 12. So watch out for distributing mistakes in problems like this. All right, 2. 2 seems to be some foiling. We've got 2x minus 3 and 3x plus 1. All right, so 2x times 3x is going to be 6x squared, and 2x times 1 is 2x, and minus 3 times minus 3x is minus 9x, and minus 3 times 1 is minus 1. Look, like terms to combine. So we end up with 6x squared minus 7x minus, that's not a, that's a, minus 3. All right, so there's our second problem. Our third one says 3x plus 2, 3x minus 2. Again, I see the difference of squares pattern, a plus b, a minus b, and I know that's going to turn into this one squared minus this one squared. But if you're not sure about that, or you're not feeling like you recognize this difference of squares and don't want to jump right to 9x squared minus 4, then by all means, FOIL. So we've got 3x times 3x, 3 times 3 is 9, x times x is x squared, so we have 9x squared plus 6x minus 6x, 2 times negative 2 is minus 4. And then these cancel because they're opposites, and I'm left with that. All right, that was problem 3. Let's take a look at 4. 4 says 3x plus 2 squared. And, you know, at this point in your math career, if you turn this into 9x squared plus 4, yeah, that's, I got the pool noodle for you. Watch out. Yeah, I don't want it to come in contact with your head because you were too busy thinking, oh, no, I think that's a very reasonable thing. No, it's not a very reasonable thing, so don't do that. Instead, what I've learned since middle school is that this is 3x plus 2 times 3x plus 2. And when I FOIL this out, I'm going to get 9x squared plus 6x plus 6x plus 4, or 9x squared plus 12x plus 4. This is a perfect square trinomial. Remember, we talked about those when we were in the factoring section, and I knew I was looking at a perfect square trinomial because that's a perfect square, that's a perfect square, and the middle term is the square root of this times the square root of this times 2, and that's what that is. 3 times 2 times 2 is 12. So I certainly, if I recognized it here or here, could have used that pattern, but in a pinch, when I don't, I can always FOIL. It's just going to take me a little longer. All right, the last problem, 2a plus b to the third. I think you should do 2a plus b to the third. So why don't you pause the video, give 2a plus b to the third a chance, see if you're comfortable doing it. All right, welcome back. I hope you didn't come up with 8a to the third plus b to the third, because that's wrong. That's the same thing as this person up here, which is wrong. You need to think about this as 2a plus b times 2a plus b times 2a plus b. And the way we handle this is we FOIL 2 of them together. So when I do that, I'm going to have 4a squared plus 4ab plus b squared. Even though I FOILed these two together to get this, I still have one more that I need to multiply through. And I see 2 terms here and 3 terms here, and that tells me that when I finished multiplying these times these, I should have 6 terms before I combine like terms. So let's see if we can get that. Okay, so we've got this last step to do, 2a plus b times 4a squared plus 4ab plus b squared. So foiling. 2a times 4a squared will be 8a to the third. 2a times 4ab will be 8a squared b. 2a times b squared will just be 2ab squared. Plus, now I'm going to do b times 4a squared, and that's going to be 4a squared b. And then I'm going to do b times 4ab, and b times b will be b squared, so I'll have 4ab squared. And then I'm going to have b times b to the second, so I'll end up with b to the third here. So, combining like terms, there are some like terms, there are some like terms. I will have that 8a to the third, but I'll also have 12a squared b, and I'll have 6ab squared, as well as the b to the third. So I had 1, 2, 3, 4, 5, 6 terms, because 2 times 3 is 6, and then I was able to condense it down to 4. Now my recommendation is that you might think about how many terms should I have before you start the foiling, because if you know there are supposed to be 6, but you only find 5 after foiling, that tells you missed something, because you're thinking about how many terms there should be and how many you got. If you don't actually do the part where you think about how many terms there should be, you're not going to notice if you missed one. All right, so please think about these problems as you do them. And that was the last one on Station 3. I wonder what Station 4 holds for us. Station 4. Station 4 is all about factoring. Ooh, factoring. All right, so you're supposed to be comfortable factoring all these things for our assessment that's coming up. We've got p to the 8th minus q to the 8th. I hope you thought, oh, 2 terms. Is there any GCF factoring? No. Is this a difference of cubes? No. Is this a difference of squares? Yes, it is. So I can think of this as p to the 4th squared minus q to the 4th squared. And because I can rewrite these as something squared minus something squared, I know that this is going to factor like a difference of squares with these values. This is my a, this is my b. So I'm going to have p to the 4th minus q to the 4th and p to the 4th plus q to the 4th. Well, that's not a difference of squares, but that is, so I can take this further and write p squared minus q squared times p squared plus q squared times, don't lose that, p to the 4th plus q to the 4th. All right, so I can't factor that without imaginaries. I can't factor that without imaginaries, but what do we have here? Another difference of squares. All right, so this one's going to be p minus q, p plus q, p squared plus q squared, p to the 4th plus q to the 4th. Ta-da! That's completely factored. Now, on the assessment, it's going to say to factor completely, and if you stop here, I mark the problem wrong, because look how much more factoring you have to do. So please, when you're doing these factoring problems, I know I said it in the factoring videos, just take a second look when you're done to make sure that really there's no more factoring and you haven't missed anything. If you don't actually look for that, you probably will miss a lot of factoring. Okay, I've got x to the 5th minus 4x to the 3rd plus 8x squared minus 32. All right, what are you thinking? Can we do any GCF factoring here? Well, I could take x's out of these, but not that. And I could take 2's out of these, but not that. So I don't see any GCF factoring here. So what can I do? That's right. When I have 4 terms, I should think about grouping. So what can I factor from the first pair? They both have x to a power, and remember we take out the smallest power. What am I left with? 5 minus 3 is 2. Then we have our minus sign. And what about here? When I factor out that x to the 3rd, that cancels, but I still have a 4. All right, and what can I take here? How about an 8? And so I'll be left with x squared minus 4. That's very reassuring, isn't it? So let's factor out that x squared minus 4 from each of these two terms. And what's left over? X to the third plus 8. Hey, are we done? No, not done yet. This is a difference of squares. Remember, when you think you're done, go back and look again. This is a difference of squares. It's a thing squared minus 2 being squared. This is a difference of squares, and it factors as x minus 2, x plus 2. Now what about this? That's a sum of cubes. And you'll remember in the video I made about factoring with sum and difference of cubes, I said you really need to memorize this pattern because you're not going to be able to just make it up in the moment. So there's my completely factored form. Now, how did I know this? Remember, we said with cubes, write it as something being cubed plus something being cubed, and then these objects go here, and this sign goes here. So these are the cube roots of these things. They go here. This one is this one squared. This one is this one squared. And the middle term is this times this, change the sign. So instead of a plus, we have a minus. Here's our completely factored form. And because there are some really fabulous students out there who see this trinomial and say, Mr. Gupta, can't we do something with that trinomial? We cannot factor that trinomial without introducing imaginary numbers. Okay, let's move on. We've got problem number 3. And it says 8x to the third plus 64y to the third. Will you please do this problem? Come back when you're done. Don't forget to pause the video. Or come back when you have questions. Okay, so, the first thing we do with all factoring problems is GCF. So I've got x to the third plus 8y to the third. Now what? Well, hopefully you recognize that this is x being cubed plus 2y being cubed. And this is a sum of cubes. So how did that factor in the last problem? This one plus this one. And then we've got this one squared. And then over here at the end, we have this one squared. It's not just y squared, but the 2 gets squared as well. So we have 4y squared with a plus. And then the middle term was this times this, change the sign. So minus 2xy. All right, don't lose that. That needs to be present at the end as well. Now, some students like to do this problem where they recognize 8x to the third plus 64. They say, oh, well, that's 2x being cubed minus 4y being cubed. And they say, okay, so when I start my factoring, that will be 2x minus 4y times this one squared. Over here, we're going to have this one squared. And the middle term is going to be this times this, change the sign, plus 8xy. But here's the thing. I'm not done, because I have GCF factoring here, and I can pull a 4 out of each of those. I have GCF factoring here. So I'm going to take a 4 out of this one, a 2 out of this one, and that's where that 8 comes from. If you leave your answer like this, it's not factored completely. Come on, you've got to look at this stuff when you think you're done and say, any more GCF factoring? Can I factor that trinomial, right? Do some thinking here. That's what you need. Okay, how about number 4? Number 4 says 2x squared minus 4x minus 8. Okay, I'm going to go the long way because even though I myself am pretty comfortable with 2 and 4. No. Oh, does this not factor? Factors of 16, negative 16 that add up to negative 4. So how about negative 1 and 16, negative 2 and 8, negative 4 and 4? None of those add up to 4. Oh. So the only thing I can do here is pull out a 2. x squared minus 2x minus 4. I mean, I can try and factor this further. These signs have to be opposites for this to be negative. But if I do minus 2x and plus 2x, the middle term cancels, and that's not bad. What if I did 4 and 1? Then, then I would have minus 4x plus 1x. That would be minus 3x, not minus 2x. So the only thing I can do here is this, unless I copied the problem down wrong. So let's take a look at this problem. I see number 4. Yep, just that. That's all I can do is the GCF factor. I wonder how many people I could catch with this who actually think they can factor that trinomial. Problem number 5, the last one on this station, is x to the 4th minus 7x squared plus 10. Remember, this is going to follow the same pattern as this one, and this one factors as x minus 5 times x minus 2. So now how does that one factor? Well, see that x? That's what's here and here. So what do we have there? We have an x squared. So ours is going to be x squared minus 5 and x squared minus 2. Now it is possible to write these as a difference of squares, but that would have us doing x minus root 5, x plus root 5, x minus root 2, and x plus root 2. I'm not expecting anyone to do that, though it would be nice. I would smile if you did that, but I wouldn't mark it wrong if you stopped here, because we can't factor this further with whole numbers, okay? And that's really our litmus test for factoring. Can we factor with whole numbers? All right, station 5. Station 5 is more factoring practice. So let's take a look at the first problem here on station 5. First problem says x to the 3rd plus 6x squared plus 9x. All right, pause the video, give that one a try, come back when you're done. Welcome back. So I start with GCF factoring. And then I say, oh, look, a perfect square trinomial, a thing squared, a perfect square here, and this one is the square root of this times the square root of this times 2. So I get x, x plus 3, x plus 3, or if you prefer, x times x plus 3 squared. Either one of those would be great. All right, problem number 2. What are we going to do here? 3x to the 3rd plus 2x squared minus 27x plus 18. Can I do any GCF factoring here? No. So what can I do when I see 4 terms? Well, 4 terms should say, let's do some grouping. Would you please finish factoring this and come back when you're done or have questions? Welcome back. I'm going to take an x squared out of each of these, give me 3x plus 2. And I'm going to take a negative 9 out of each of these, leaving me 3x minus 2. Oh, minus? No, plus. Wait, taking the negative out? These signs, there's something wrong with the signs. Did I copy it down wrong? I did not copy it down wrong. Oh wait, there's a note on the station. It says, it's subtraction. Oh yeah, that is supposed to be minus. There we go. So I take out the negative 9, and I end up with a positive 2. I see 1 term, 2 terms joined with subtraction. Did those 2 terms have anything in common? Sure do. So let's factor out that 3x plus 2. And what's left over when I do that? Well, I get x squared minus 9. Okay, is there anything we're missing? That's right. Good. Nice. That's a difference of squares. So we still have to take this further. It's going to be x minus 3, x plus 3. All right, so please, when you think you're done with the factoring, go back and look again. Like a lot of people, stop here. Oh my goodness, you just did so much work to get to this place only to have the problem marked wrong, because that's a difference of squares and you can take it further. It's not that you don't know how to factor, It's that you're not looking when you think you're done and asking the question, is there still more factoring? All right, problem number 3. 3 says 27x to the third minus 125y to the third. Okay, pause that video, give this one a try. Well, so I see this as 3x being cubed minus 5y being cubed. And because this is a difference of cubes, I know I'm going to have a binomial and a trinomial. The binomial is this minus this, 8x minus 5y. This one is that squared. Remember, it's squaring the 3 and the x, so we have 9x squared. This one is this one squared. Minus 5y times minus 5y is plus 25y squared. And what about our middle term? Our middle term is this times this, change the sign. So plus 15xy. All right. This is not factorable, and there's no GCF factoring I can do here. So I think we're all done. Let's take a look at problem number 4. Problem number 4 says 6x squared minus 17x minus 14. Okay, so if I'm going the long way, 6 times 14 is negative 84. And what are the factors of that? Well, negative 1 and 84. Negative 2 and 42. Does 3 go into that? It sure does, because these digits add up to a number divisible by 3. So negative 3 times 28. And, oops, I don't want that. What else? How about 4? 4 goes in, negative 4 times 21. We know negative 6 times 14. Negative 7 times 12. And then it's just going to be these again, but the negatives go on those numbers. Okay, so do any of them add up to negative 17? That's a 28. There we go. If I do 6x squared minus 21x plus 4x minus 14, I should be good to go, because these add up to that and multiply together to be this times this. So I'm going to factor by grouping, and here I've got a GCF of 3x, leaving me 2x minus 7, and here I've got a GCF of positive 2, leaving me 2x minus 7. I have one term, I have two terms joined by that addition sign. Do those two terms have anything in common? Yeah, this 2x minus 7 and this 2x minus 7. So let's factor out a 2x minus 7. What's left over? This is, and this is. All right, is there any more factoring here? No. Now, if you can do this one with guess and check, great. Use guess and check. You don't have to do the long way. I'm showing the long way because if you're still struggling with factoring, then you need me to take the long way and show you how to do it. But if you're good with guess and check on problem number 4, use guess and check. Remember, it's not just guess, though. It's check. So when you're done, especially on an assessment, you might want to go back and see if it foils to what it's supposed to be. 48 squared. Okay. Is that a difference of cubes? No, because these are squared things. Is it a difference of squares? Well, that's not a perfect square, and that's not a perfect square. But what should I be doing? What should I always do first? GCF factor. It goes into both of these, and I will tell you 3 does. So I'm going to have 25x squared minus 16y squared. And now look, I have something squared. I have another thing squared. This is a difference of squares. It's 5x being squared minus 4y being squared. And so my pattern is going to be 5x minus 4y times 5x plus 4y. There's my factored form. Don't forget to do GCF factoring first, please. All right. And that was it for station 5. Let's move on now. Station 6. Station 6 is solving equations, and these look like ones that I'm supposed to factor. Let's see if that's true for station 5, if all of these problems can be solved by factoring and setting factors equal to 0. I've got 2x squared plus 5x minus 12. Okay, so that's going to be 2x and x. Now, what about this? Well, there's lots of different things. 1 and 12, 2 and 6, 3 and 4. So we're just going to have to, well, wait a second. They should, one of these is negative, negative 4, positive 3, negative 6, positive 2, negative 12, positive 1. Do any of these add up to positive 5? These add up to 1. These add up to negative 1. These add up to 4. These add up to 11. Hey, guess what? It doesn't seem to factor. Oh, I left out the 2. See, you can't leave out that 2. Okay, so 2 times negative 12 is negative 24. That adds up to positive 5. And how about negative 1 and 24? No. Negative 2 and 12? No. How about negative 3 and 8? Ooh! So I can replace this term plus 8x minus 3x minus 12 with these two terms, and now I've got 4 terms, and I'm happy about that because now I can factor by grouping. From the first pair, we can take out a 2x, leaving us with x plus 4. From the second pair, I'm going to take out a negative 3, not just a positive 3, and negative 3x divided by negative 3 is x. Negative 12 divided by negative 3 is positive 4. And look, these are the same. So let's factor out that x plus 4. And what will be left? This 2x and this minus 3. All right, so there's our factored form for problem number 1. How about problem number 2? 2 says 2x to the 4th plus 5x squared minus 12. Wait, didn't I just factor that? Oh, we're solving. Oh my goodness, let's go back to that last problem. So that's a 4, and that's a 2x, and that's an x, and that's 8, 3 minus plus. Okay, so that's minus 3x plus 8x is going to be plus 5x. There's my minus 12. Remember, we're solving, so we're not done yet. We have to set each factor equal to 0. So here I'm going to have 2x equals 3, or x equals 3 halves. And I have to subtract 4 from both sides, so I get x equals negative 4. Is this one of our must checks? No. Polynomials are always ought check. I ought to check that. They're not must checks. We do have 3 must checks. Remember, first one, no zeros in the denominator. So if we have x stuff on the bottom, that's definitely no zeros in the denominator when we're done solving. 2, if you square both sides of an equation while solving, that's a must check. And finally, number 3, when we have absolute value equals x stuff, that's also for us a must check. We must check those answers. But that's not what we have here. What we have here in problem number 2 is 2x to the 4th plus 5x squared minus 12 equals 0. So, hey, this looks a lot like problem number 1 with 2x squared plus 5x minus 12. This is twice this power, this is twice this power, and 2 and 5 and negative 12. So, I think since I know how to factor this, 2x, x plus 4 minus 3. Since I know how to factor this one, I should be able to apply that same pattern, except instead of x's here, like this is an x, I'm going to have x squareds. So I'm going to have 2x squared minus 3 and x squared plus 4. Now what are we supposed to do? Well, we're supposed to set each factor equal to 0. X squared plus 4 equals 0. X squared equals negative 4. Uh-oh, I can't take the square root of a negative, so that doesn't produce any real solutions. But 2x squared minus 3 equals 0, or x squared equals 3 halves, then I can take the square root of both sides, and what am I not supposed to forget? That's right, I'm not supposed to forget that plus or minus. Plus and minus root 3 halves. Now, I will tell you that this answer bothers me a lot. I think it's kind of funny that I'm actually at a place in life where that bothers me. But that bothers me. I won't mark it wrong on a quiz or a test, but really it bothers me. And so when I see plus and minus square root of 3 halves, I would really prefer you to write that as plus and minus root 3 over root 2. And then, if you feel really compelled, and I don't know that I need this step, but I would rationalize the denominator, plus or minus root 6 over 2. I think that's prettier than that. Yeah, but that's me. Okay, and then the last one, problem number 3. Will it be the same pattern? Well, let's take a look at problem number 3. It says 2x to the 6th plus 5x to the 3rd minus 12 equals 0. And oh my goodness, look, it's the same coefficients, and this power is half of that power, and the signs are still the same. So how's that going to factor? Well, 2x, look here for the power, to the 3rd, x to the 3rd, and then we have our minus 4 and our plus 3. No, we have a plus 4 and minus 3, right? It's called guess and check. So I had to actually check to realize that wasn't going to work originally. So please don't be afraid to actually check when you're using guess and check. All right, so now what? Well, this is supposed to equal 0. X to the 3rd plus 4 equals 0. X to the 3rd equals negative 4. And x equals the cube root of negative 4. And by now, we really need to know that we can take the cube root of a negative number. Think about that graph. There's our cube root graph. Look over here. Here's negative 4. Is there a y value there? Sure is. So this must be a real number. Now, if this was squared, x squared plus 4, no, I couldn't do that with real numbers. Don't forget to set this factor equal to 0. So I get x to the 3rd equals 3 halves. I take the cube root of both sides. And so I get x equals cube root of 3 over 2. And yeah, it does, I still don't like a fraction under there. I wouldn't mark this wrong unless you put the plus or minus there. But I would probably write it as cube root of 3 over cube root of 2. And then I'd rationalize the denominator with 2 more 2's. That's 4 with the cube root there. And so my final answer would be x equals cube root of 12 over 2. And this one over here, cube root of negative 4. All right, so those are my 2 answers for the third problem on station 6. And the third problem was also the last problem. So let's move on to station 7. We've got 14 to get through, so let's gee up. All right, oh look, absolute value equals x stuff. That's a must check. All right, remember, when you talk about absolute value, you can't write the positive and negative components until you've isolated the absolute value. And we will see that in problem number 2. Problem number 1, though, absolute x minus 10 equals x squared minus 10x. Okay, the absolute value is isolated. There's nothing else over there with it. So I'm going to write the positive component, which is just x minus 10 equals x squared minus 10x. But I'm also going to write the negative component. Remember, to make the negative component, we have to change both signs on one side. And I always change these signs. So I'm going to have x minus 10 equals negative x squared plus 10x. Oops. Plus 10x. All right, let's solve each of these. I see an x squared, so I know I want to move everything onto one side. So this is going to be equal to 0. X squared minus 11x plus 10. that's going to factor as x minus 10, x minus 1. When I set each factor equal to 0, I get x equals 1 and x equals 10. Why don't you do this one? Come back when you're done. Okay, I moved my stuff over here. I got x squared minus 10x minus x minus 10 equals 0, or x squared minus 11x minus 10. This came over here. That's a plus x. So that's going to be minus 9x. That's better. Equals 0. And then this factors as x minus 10, x plus 1. Don't worry, if you moved everything over here, you're still going to get the same solution. Our intermediate steps will be different, but you should get x equals 10 and negative 1. So I've got 3 numbers to check. I've got 1, negative 1, and 10. This is definitely a must-check situation because I have absolute value equals x stuff. So let's plug the numbers in. 1. 1 minus 10 is negative 9. The absolute value of negative 9 is 9. And I plug in a 1 here and a 1 here. 1 squared is 1. 10 times 1 is 1. 1 minus 10 is negative 9. 9 does not equal negative 9, so it's not one of my solutions. How about 10? 10 minus 10 is 0. Absolute value of 0 is 0. 10 squared is 100. 10 times 10 is 100. 100 minus 100 is 0. So this 0 does equal that 0. So this is one of my solutions. And what about negative 1? Well, if I plug in a negative 1, minus 1 minus 10 is minus 11. The absolute value of minus 11 is plus 11. And now I'm plugging in a negative 1 here. Negative 1 times negative 1 is positive 1. Negative 1 times negative 10 is positive 10. 1 plus 10 is 11. So both of these work. My solutions are x equals negative 1 and 10. Okay? Remember, you could also think about this graphically. Yeah, I'm going to keep saying it. I know absolute value of x minus 10 looks like this, 0, 10. And I know that x squared minus 10x is an up-pointing parabola with x-intercepts at 0 and 10. So, and here's one solution, and here's the other solution. This one, it turns out, is at negative 1, and this one's at positive 10. So when I think about these things graphically, that can be a quick and easy check, especially if I've been practicing my graphing and thinking about graphing so that it's easy and it comes to mind while I'm doing a problem like this. Okay, problem number 2, we've got 2 absolute 2x plus 1 equals 19. So do I write the positive and negative components now? No, I do not. I need to isolate the absolute value first. Okay, there can be nothing on this side except the 2x minus 1 before I write the positive and negative components. So if you haven't done this problem yet, please pause the video, give it a try, because this is definitely test-worthy. So I'm going to subtract 1 from both sides and get 18 over here. I'm going to divide by 2 on both sides and get 2x plus 1 equals 9. It's only now that I can write the positive and negative components. The positive component will be 2x plus 1 equals 9, or 2x equals 8, or x equals 4. The negative component, however, I have to change the sign. Or I could change both of these, but I'd rather just change 1. So I'm going to have 2x plus 1 equals negative 9. So I'm going to subtract 1 from both sides and get negative 10 equals 2x. And then I'm going to divide everywhere by 2 and get x equals negative 5. Now remember, this is a must-check problem. Oh, no, it isn't. There's no algebra stuff over there. No, this is just an ought check. I ought to plug this back in, but I'm probably not going to. But on a test, yeah, I actually probably would. So I'd have 8 plus 1 is 9. The absolute value of 9 is 9. 9 times 2 is 18. Plus 1 is 19. That works. What about a negative 5? 2 times negative 5 is negative 10, plus 1 is negative 9. The absolute value of negative 9 is 9. 9 times 2 is 18, plus 1 is 19, and that one works as well. So I've got two solutions there. All right. And then the last one here on station 7, problem number 3 says 2x plus 3 minus 1 equals negative 5. All right, so we're going to add 1 to both sides. 2x plus 3 equals negative 4. And then I need to write the positive and negative components. All right, so 2x plus 3 equals negative 4. And that's the positive component. The negative component, 2x plus 3 equals, change the sign, 4. So if I solve here, what's going to happen? I'm going to have 2x equals negative 7, or x equals negative 7 halves. And then over here, when I subtract 3, I'm going to have 2x equals 1, or x equals 1 half. Now, just out of curiosity, let's plug these back in. So 2 times negative 7 halves is negative 14 halves, which is negative 7. Negative 7 plus 3. Negative 7 plus 3 is negative 4. The absolute value of negative 4 is 4. 4 minus 1 is 3. That doesn't equal this. What if we plug in a 1 half? 2 times 1 half is 1. 1 plus 3 is 4. The absolute value of 4 is 4. 4 minus 1 is 3. Well, that's not true. No solution. Wait, this isn't absolute value equals x stuff. What's the deal? Well, what's the deal? Hey, did you think about it graphically? So this shifts the graph left 3. This squishes it horizontally. But what's that do? That shifts the graph down 1. And so my graph is over here at negative 3 halves, common negative 1. There's my absolute value. Okay, what's that? That's a horizontal line. Y equals negative 5. Does this line ever intersect this absolute value, v? No. No, it doesn't. This is no solution. Oh my god, maybe I should just check all absolute value problems. Well, you could, except here's what I'm going to say. Absolute value can't equal a negative, right? I mean, think about that. I've got an absolute value of x. Is the result of plugging in any x value in here going to be a negative number? No, because this turns everything positive. So unless this is more negative than that, these things are never going to intersect. All right, so remember that intermediate step where we added 1 and we said 2x plus 3 equals negative 4? Absolute value can't equal negative. So I should know from here that it's not going to be the case. But you're more than welcome to go and solve it out. Just remember, you gotta must check this. All right, that was station 7. Station 8. Station 8 seems to be about solving inequalities. Oh, I remember inequalities. Station 8. Inequalities. 1. 10 minus 7x is less than 4 plus 2x. Do you remember what I said with inequalities? First thing you do, change that to an equal sign. Then apply your Algebra 1 skills to solve this linear equation. Linear because these are both x to the first. I'm going to move my x's over here and my not x's over here. So 6 equals 9x, because I'm adding 7x to 2x to get 9x. And then I'm going to divide by 9, and that's going to give me x equals 2/3. All right, now that's not my answer. That's my critical number. I put that on my number line. Can't be equal to, so that gets an open circle. Let's try 0 and 1. If I plug in a 0 here, I get 10 minus 0 is 10. If I plug in a 0 here, I get 4. So I've got 10 is less than 4. No, it isn't. What if I plug in a 1? 7 times 1 is 7. 10 minus 7 is 3. is 3 less than, I'm plugging in a 1, 2 times 1 is 2, plus 4 is 6. Is 3 less than 6? Yes. So, what's my solution look like? Well, parentheses, 2/3 to infinity. That's my solution. Remember, your solution to inequality is almost always going to be domain interval. All right, next, number 2. We've got absolute 4x plus 7 is less than 21. Again, we could think about this stuff graphically. Here's negative 7/4. There's that absolute value. Here's the line y equals 21. And oh, look, I expect to find 2 points of intersection. It didn't really take very long for me to know that there should be 2 answers here. Remember, the first thing I want to do is turn that into an equal sign and write my positive and negative components. My positive component, 4x plus 7 equals 21. My negative component, 4x plus 7 equals, change the sign over here, negative 21. So I'm going to now solve for x in each of these cases. Subtract 7, divide by 4, x equals 14 over 4, or 7/2. What about here? I'm going to subtract 7 and get 4x equals negative 28, or x equals negative 7. This is an inequality, so these aren't my answers. These are my critical numbers. Negative 7, positive 7/2. So we need to check values on each of these 1, 2, 3 intervals in the original inequality to see if each of these intervals is part of my answer. So a number between negative 7 and 7/2, well, I like 0 because it's easy to work with. I need a number bigger than 7/2 or 3.5, so I'm going to go with 4. And over here, how about negative 10? All right, so negative 10 times 4 is negative 40. Negative 40 plus 7 is negative 33. The absolute value of negative 33 is 33. Is 33 less than 21? No, it is not. What if I plug in a 0? So this goes away and I get 7. The absolute value of 7 is 7. Is 7 less than 21? Yes. And what about if I plug in a 4? 16 plus 7 is going to be 23. The absolute value of 23 is 23. Is 23 less than 21? No. And because this is not equal to, I know this is a no and this is a no, because these would actually be equal. This would give me 21 when I plugged in here. This is 21, and so I'd have 21 equals 21, but I need 21 less than 21, and that's not true. Okay, so what's my solution look like? Well, it goes from here to here, negative 7 to 7/2, and both ends get parentheses. Okay, last problem on station 8 says 10x squared plus 11x is greater than or equal to 6. And oh my God, don't be this student who does this. Please, please, please don't be this student, because that is fooling with upward action. Okay, please, no, 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 no. I like that equal sign, but no. You're going the wrong way. You got 10x squared plus 11x equals 6, and then you move the 6 over. So I've got 10x squared plus 11x minus 6 equals 0. Okay, so can we do some factoring here? The factors of negative 60 that add up to positive 11. So 5x, 2x, 3, 2, plus, minus. Positive 15 minus 4 is going to be positive 11. Okay? I'm kind of wondering if you want me to go through with the long way, but I'm not going to. So if you want me to do it the long way, by all means, send me a message in GroupMe or ask in the Zoom. Don't forget to ask that question. Okay, so now I'm going to get x equals 2/5 and x equals negative 3/2. I put those on my number line, negative 3/2, 2/5. And remember, I'm not going to be worried about these fractions because I can test whole numbers. I just have to make sure my integers are actually in the intervals. Okay, if I plug in a -2, remember we go back to the original inequality. I plug in a -2. -2 times -2 is +4. 4 times 10 is 40. -2 times 11 is -22. And that's going to be 18. Is 18 greater than or equal to 6? Yep. What about 0? So then I'm going to add 0 plus 0. Is that greater than or equal to 6? No. And if I plug in a 1, I'm going to get 10 plus 11 is 21. Is that greater than or equal to 6? Yes. And you know what else are yeses? 2/5 and -3/2 are both going to be yeses. And I can either test the points or I can see could be equal to, and so those are included as well. So what's my solution going to be here? Well, that's no problem. That's -infinity to -3/2 with a bracket, because this point here was a yes, and then union from here to infinity, and this point is included. So not a parenthesis, but a bracket, 2/5 to infinity. So that's my answer to number 3 on station 8. Let's take a look on station 9 now. Station 9 is all about solving other types of inequalities. So let's go. We've got x. Oh, this is station 9. We're doing problem 1, which is x minus 3 less than or equal to 10. Really, I'm trying to see who's going to fall for this one, because I'm going to get a lot of people who do x equals 10 and x minus 3 equals 10, so x equals 13. Yeah, no. This is x squared minus 3x minus 10 equals 0. Move everything over. Now factor. I've got x minus 5. I've got x plus 2. And so my critical numbers are -2 and +5. Okay? Hey, if I had done these, I would have said x equals 10 and x equals 13. Guess what? That's not correct. So you can't do that. Don't set these factors equal to 10. Move everything onto one side, distribute, then factor. Okay, so we've got these two critical numbers. I'm going to do 0 and 6 and -3. When I plug in a -3 in the original equation, -3 minus 3 is -6. -6 times -3 is +18. Is +18 less than or equal to 10? No, it is not. What if I plug in a 0? If I plug in a 0, 0 times -3 is 0. Is that less than or equal to 10? Yes, it is. And if I plug in a 6, 6 minus 3 is 3. 3 times 6 is 18. Is that less than or equal to 10? No, it is not. See the equal to sign? Well, that means that's a yes, and that means that's a yes. So my answer is -2 to 5 with brackets on both ends. Alrighty. So let's take a look at problem number 2. Problem number 2 says 3 over 2x plus 3 less than 1x minus 2. Okay, so the first thing I do is I, of course, change that to an equal sign. And now I'm going to multiply everywhere by x minus 2, 2x plus 3, x minus 2, and 2x plus 3. So those cancel. I have 3 times x minus 2. Don't forget to distribute that 3 to the -2. And over here, these cancel, and I have 1 times this, so I get 2x plus 3. And so now I move the x's there, and the numbers there, and I get x equals 9. Is x equals 9 my only critical number? Well, remember in the video about solving these rational inequalities, I showed you that critical numbers is where something critical is happening on the graph, and that can occur with solutions, but it also occurs with denominators. These are going to be vertical asymptotes. These are places where the function can't exist. So I actually have 3 critical numbers here. This one makes -3/2, and this one makes x equals positive 2. Okay, so let's get our number line going. We've got negative 3 halves, we've got 2, we've got 9. Those are our three critical numbers. And let's test intervals with 0, with 3, with 10, with negative 2. All right, so when I plug in a negative 2, I'm going to have 2 times negative 2, which is negative 4, plus 3 is negative 1. 3 divided by negative 1 is negative 3. And over here, when I plug in negative 2, I have 1 over negative 4. So is negative 3 less than negative 1/4? Well, remember, less goes that way. There's negative 3. There's negative 1/4. Why, yes, negative 3 is less than negative 1/4. And so that's going to be a yes. Now, what if I plug in a 0? So this goes away, and I have 3 over 3, which is 1. And this goes away, and I have negative 1/2. Is 1 less than negative 1/2? No, it is not. Okay, and sometimes these alternate, and sometimes they don't. So please don't assume that they will always alternate. Instead, take the time to plug that 3 in there. 3 times 2 is 6. 6 plus 3 is 9. 3 over 9 is 1/3. All right, and then we have our less than. And what if we plug a 3 in here? 3 minus 2 is 1. 1 over 1 is 1. Is 1/3 smaller than 1? Yes. And what if I plug in a 10? I have 3 over 23. Is that less than 1 over 8? Well, I don't know. They both look kind of small. But if I cross multiply, these cancel, I get 8 times 3 is 24 is less than 23. Is that true? No. No, it's not true. So this is a no. Now, what about these points? Well, remember, it's never going to be yes for a critical number that came from a denominator. And this says not equal to. If I had this, this would be an open circle, this would be an open circle, and this would be a closed circle. So I'd have no, no, yes. But because I have that, all of them are no's. So here, negative infinity, not this point, you go up to the critical number to negative 3 halves with a parenthesis, union here, 2 up to 9, both with parentheses because they're not included. Okay, so please remember, with rational inequalities, you've got to also get critical numbers here, not just from solutions. Okay, the last problem on station 9 is this one. Number 3 says x to the third is greater than x to the second. Well, you know, this is x to the third minus x squared equals 0, right? I have to turn that into that, and because this is a polynomial, I'm going to move everything to one side. I factor out an x squared, I have x minus 1, okay? And now I've got two critical numbers. This is x equals 1, x minus 1 equals 0, I add 1, I get x equals 0. This one is x squared equals 0. I take the square root of both sides. The square root of 0 is still 0, and the square root of x squared, we're going to have x. So I've got two critical numbers here, 1 and 0. So if I put in a 0 and I put in a 1, and then I test those intervals with 2, 1/2, and negative 1, let's see what happens. Okay, if I plug in a negative 1, negative 1 to the third is negative 1 times negative 1 times negative 1, which is negative 1. Negative 1 squared is 1. Is that a true statement? No, it is not. If I plug in a 1/2, 1/2 times 1/2 times 1/2 is 1/8, as opposed to plugging in the 1/2 here, which is 1/2 times 1/2, or 1/4. Is 1/8 bigger than 1/4? Why, no, it's not. An eighth of a pizza is half as much as a quarter of a pizza, so that's also a no. Look, they're not alternating. And if I plug in a 2, 2 to the third is 8, Is 8 greater than 2 squared or 4? Yes, it is. And if I plug in a 0, is 0 bigger than 0? No. If I plug in a 1, is 1 bigger than 1? No. So I end up then saying 1 to infinity. Please don't write 2 to infinity. It's not the test point. It's the critical number. You have to use your critical numbers in the answer, not these random points that you tested, okay? Because the points you test may be different from the points I test. We want to be able to include everything up to positive 1. It's just not including positive 1. But 1.00001, yeah, it would be true for that too. It's going up to 1. All right, so that was station 9. More inequality fun. Excellent. What about station 10? Ooh, solving. No inequalities, just straight solving. We've got some rational equations to solve, and it looks like a quadratic to solve. So I've got station 10. I've got, for problem number 1, x minus 3, x plus 2 equals 14. And I will chase you with a pool noodle when we see each other live. If you say x minus 3 equals 14 and x plus 2 equals 14, that will make me very, very sad. Okay? Oh my god. Can that get better? That's slightly better. Need some more light. Why is that so thin? Am I having glaucoma? Alright, I hope not. So, let's try a different one. I think this is my last thick one. So, yeah, don't do that. Don't be this person. If you're this person, you're going to get the problem wrong. Okay? You can only set factors equal to 0. That's not 0, so you're not done. How are you supposed to do this? Well, FOIL it out. X squared minus x minus 6 equals 14. And because it's a quadratic, you've got to move everything over. X squared minus x minus 20 equals 0. Now you can factor x minus 5, x plus 4, and set each factor equal to 0 to get x equals 5 and x equals negative 4. Again, think about this problem graphically. Okay, if I think about this problem graphically, this is a parabola with x-intercepts at 3 and negative 2. Negative 2, 3, up pointing parabola. And then I want to know when that intersects y equals 14. Well, twice. I just have to find where those are. One, something smaller than negative 2, and one, something bigger than 3. Okay? Okay. How about problem 2? I feel like I have to switch to these ultra fine points. I need to go get some more markers. Sorry about this. X minus 2 over x plus 2 plus 4 over x plus 2 plus 4 equals 0. Now, it would be really nifty if you said, hey, these are common denominators. Let's add them and have x plus x minus 2 plus 4, x plus 2, and then say, oh, look, that's going to be x plus 2 over x plus 2 plus 4 equals 0. And a number divided by itself is 1. Does 5 equal 0? No, it does not. And as a result, this has no solution. That's the fast way to do this problem. A slightly longer way, but will always work way is, hey, I see this denominator here. The first thing I want to do is multiply everywhere by that denominator, including here and here. I multiply everywhere by that denominator. Okay, so here these cancel. I have x minus 2, then the plus sign. These cancel, giving me 4 plus, 4 x plus 2 equals 0 times this stuff is still 0. So I've got x minus 2 plus 4 plus 4x plus 8 equals 0. And now let's combine the terms. I get 5x. I've got 12 minus 2 is 10. And so I get 5x equals negative 10, or x equals negative 2. Isn't that a solution? Well, wait a minute. This is a must check because I got x stuff in the denominator. What happens when I plug a negative 2 in there? Minus 2 plus 2 is, that's right, 0. Can I divide by 0? Oh, I can't have a 0 in the denominator, and that's what I get when I plug in negative 2, and that's why this has no solution. Okay? This has no solution. Remember, denominators. This is a must-check situation. All right, what about number 3? 1 over x minus 2 plus 3 over x plus 3 equals 4 over x squared plus x minus 6. Now, your common denominator is not this times this times this. That is a common denominator, but we want the least common denominator. And over here, look what I've got. I've got the common denominator already. So I actually have to multiply everywhere by x minus 2, x plus 3. X minus 2, x plus 3. And over here, x minus 2, x plus 3. Okay, so what cancels? This cancels this, so I have 1 times that. And this cancels that, leaving me plus 3 times x minus 2. And all of these cancel all of those, leaving me just 4. I really like multiplying everything by the common denominator and canceling, because now I don't have any fractions. I'm not saying make a common denominator. I'm saying get rid of all the fractions by multiplying everything by the least common denominator. So now I'm going to distribute, and I'm going to combine like terms, and I get x equals 7/4. Okay, is this good? Well, check it out. Did I get x equals 2? Because a 2 would turn this into 0. No, that is not x equals 2. It's a little smaller than 2. Did I get x equals negative 3? Because that would turn this into 0. No, this is not negative 3. So, because this number is neither positive 2 nor negative 3, which would turn these into 0 and this into 0, I know that's my answer. Okay? So I've got negative 7/4, positive 7/4 for the last problem on station 10. Great. Okay, station 11. What's it going to be about? Can't wait and see. There are so many topics in this unit. Station 11 is solving radical equations. I bet we'll have an opportunity to square both sides, and that's must-check number 2. Station 11. Okay, problem 1 says square root of 4x minus 3 minus 5 equals 0. Remember, we don't want to square both sides until we've isolated the radical. That means you have to get over here. So the square root of 4x minus 3 equals 5. And now the next thing I want to do is square both sides. And because I'm squaring both sides, this is now a must check. Whenever I square both sides, that's a must check. So I've got 4x minus 3 equals 25. I get 4x equals 28, or x equals 7. So let's take this 7 and plug it in. 4 times 7 is 28. 28 minus 3 is 25. Square root of 25 is 5. 5 minus 5 is 0. So that's my answer. Okay? Just because I squared both sides doesn't mean that I must have an extraneous solution. It just means that I might have an extraneous solution. Okay, problem number 2 says x equals square root of minus 1 minus 2x. Well, the radical is all by itself, so let's square both sides. And I get x squared equals negative 1 minus 2x. I see this is a quadratic, so I know I want to move everything onto one side. And now it looks like this. You need to factor this trinomial. It's a perfect square trinomial. And so when I set each factor equal to 0, I get x equals negative 1. Well, can I plug that in? Let's see. Remember, we're plugging this in into the original equation. Okay, so that's going to be negative 1. And what are we going to have over here? We're going to have negative 2 times negative 1, which is positive 2. Positive 2 minus 1 is positive 1. The square root of 1 is 1. Are these equal? No, they're not. So this has no solution. Okay? Now, I could also think about this problem graphically. There's the line y equals x. And that's the line y equals x. This is my square root graph that is, so I'm going to add 1 to the x's, which goes that way, but then I'm going to, oh, and so it goes here, like that. They come close, but this is -1 and this is +1 over here, and this is 1/2. Yes, -1/2. -1 minus 2x equals 0. Oh, -1 over here. These graphs don't intersect. Okay, a solution is a point of intersection on the graphs. All right, third one. 3 says square root of 10x minus 16 equals x. Okay, let's square both sides. And I get 10x minus 16 equals x squared. Let's move everything over. 0 equals x squared minus 10x plus 16. All right, finish up this problem. Tell me what you get. Did you then factor this as x minus 8 and x minus 2 and get x equals 8 and x equals 2? Well, I hope so, because that's what I got. All right, now let's go back to our original equation, not this squared thing, just the original, and plug these in. 8 times 10 is 80. 80 minus 16 is 64. The square root of 64 is 8. And I plug in an 8 for this x, and I get 8. 8 equals 8, so that one works. What about 2? Well, 2 times 10 is 20. 20 minus 16 is 4. The square root of 4 is 2. And if I plug in 2 over there, yep, that works great. I've got 2 solutions. And graphically, yes, I agree with those 2 solutions because I've got this graph. And then, where's my x-intercept here? So if I set 10x minus 16 equal to 0, I get 10x equals 16. I get x equals 16 over 10 or 8 over 5. And then it comes back a second time. So this is 2, and over here is 8. My square root graph crosses the line in 2 places. All right, that was station 11. Did I solve that? Yes, I did solve that. Okay. All right, what about station 12? Station 12 says, look, it's our dear friend GCF factoring. That's great. All right, station 12. You know, I really like this set of stations. It's very comprehensive, and the level of difficulty on the problems is just like, yes, this is exactly what they need to be comfortable with. 5, 2x plus 3 minus 2x plus 3 to the second. Okay, this is GCF factoring time. Why don't you give it a try? Come back if you're stuck. Come back when you're done. Okay, welcome back. I notice that these two terms have a 2x plus 3, so I'm going to factor out that 2x plus 3. What am I going to be left with from the first term? Well, I took this out, so I've got a 5. Now my minus sign. Now this is 2x plus 3 times 2x plus 3, and I factored one of them out, but I still have a 2x plus 3. Be careful. See that minus? See that minus? That minus doesn't just go to the 2x. It has to be distributed. Oh, so many people make mistakes with that. 2x plus 3 times 5 minus 2x minus 3. Or negative 2x plus 2 times 2x plus 3. All right, this is not a solving problem. I don't see equals 0 anywhere, so stop. You're done factoring. This is a factoring problem, not a solving problem. All right, number 2. It looks a little more engaging, a little more involved. 2, 3x minus 4 to the third, 2x plus 1 plus 3, 3x minus 4 to the second times 3 times 2x plus 1 to the second. All right, go for it. Come back if you have questions or want to check your answer. All right, so I'm going to take out a 3x minus 4 to the smallest power, and I'm going to take out a 2x plus 1, because I see it here and here, to the smallest power. This has a 2, this has 3's, I can't take any of those out. So what's left over? Well, this 2 is left over, and I took this out, and I took 2 of these 3 out, so I still have 1 more. Now my plus sign, and I took out both of these, so I still have 3 times 3 or 9, and I've got 2 of these, but I only took 1 of them out, so I've got 2x plus 1 here. Okay, so I've got 3x minus 4 squared, I've got 2x plus 1, and now 6x minus 8 plus 18x plus 9. Tidy this up, combine like terms, and you should have 24x plus 1 times 2x plus 1 times 3x minus 4 squared. And in Chapter 5 in Calculus, when we get to this point, we'll be solving. We'll be setting each of these factors equal to 0. Okay, there's problem 2. I hope you did well on that one. Problem 3, it's got rational exponents. Let's take a look at problem 3. It's got 1/2 2x plus 3 to the minus 1/2 times 2 times 3x minus 5 to the 2/3 plus 2/3 2x plus 3 to the, what power is that? There's a typo here somewhere. That must be a typo. To the 1/2. No, that's not right. How could that be right? X to the 1/2. Sorry, because I know the calculus. I'm wondering, is that really what it says? That's really what it says. 1/2. Is the first one minus 1/2? Oh, that's a minus 1/2. And so, yes, that should be a 1/2. My bad. Okay, and then I've got a 3 and a 3x minus 5 to the negative 1/3. Yes, negative 1/3. So that looks like a lot of fun. Well, if you define fun that way. It is still 2 terms, so why don't you do some GCF factoring and come back when you're done. Okay, so I always take the smallest power out, minus 1/2 plus 1/2. I'm going to take out the minus 1/2. And 3x minus 5 to the 2/3, 3x minus 5 to the negative 1/3. I'm taking out 3x minus 5 to the negative 1/3. So what's left over? Well, I've got a 1/2. I took out all of that. I've got this 2. And here, we factored a negative 1/3 out, right? That's all right. And then remember that this is what I'm doing. 3x minus 5 to the 2/3, factoring out or dividing 3x minus 5 to the negative 1/3. And when the bases are the same and I'm dividing, what do I do with the exponents? I subtract them. So 2/3 minus a minus 1/3 is going to be 3/3 or 1. So I'm going to have a 3x minus 5 to the 1. Now I have my plus sign, and then this 2/3. And here we factored a negative 1/2, right? That's what we took out, and the taking out is the minus. So 1/2 minus a minus 1/2 is going to be plus 1. I still have this 3, but I took this out. All right, so what do I notice here inside the brackets? Well, 2 times 1/2, that cancels. And this 3 can cancel with this 3. So now I've got 3x minus 5 plus 2 times 2x plus 3. So I still have to distribute and combine like terms. 3x minus 5 plus 4x plus 6, and that's going to give me 7x plus 1. Don't forget these guys over here. And you know, if you want to put these in the bottom and make them positive, that's fine. I'm just going to leave them on the same level, 3x minus 5, as the 7x plus 1, 2x plus 3, negative 1. So there's our answer, okay? Be careful with this step, okay? Be careful with what's left over. Be careful with your distributing. Just be careful, please. Be careful. Okay, that was station 12. We're on to 13. 13. Oh, this is not part of that problem. This goes right there. Huh. Okay. Typo time. So, station 13 seems to be about working with exponentials. So, our first problem, negative 3/5 squared times negative 2 to the third, 5 to the third. Okay? So, yeah. So I know that I'm going to apply that power to each of these. Negative 3 squared is 9. 5 squared is 25. Times 2 to the third is 8. So I have negative 8. And 5 to the third is 125. So that's going to give me negative 72 over, ooh, what is 625 times 5? 5, 2, 12, 3125. Okay, that seems like a pretty straightforward problem. I'm not sure why that's there. Let's see what the next one is. All right, 25. Oh, problem 2 says 25 to the negative 3/2 power. Well, remember, this is not a problem where you reach for your calculator. It's where you rewrite the base. If you haven't tried this problem already, please do it now. Pause the video, give it a try. Come back when you have questions or are done. Okay, so if I'm rewriting this base, that's going to be 5 squared to the negative 3/2. When I raise a power to a power, I multiply them. 2 times negative 3/2 is going to be negative 3. So this turns into this, or this, which is that. Okay, so I like that answer for number 2. Number 3 will give you some more practice in that, so you should definitely do this one. We've got 64 to the negative 4/3. Okay, rewrite the base, simplify this expression. Welcome back. Did you remember that 64 is um, 64 is the same as, well, I mean, it's a lot of things. It's 2 to the 6th, it's 4 to the 3rd, it's 8 squared. Which one do I want? That one. Why? Because look at my power. I want to take my exponent and multiply it by negative 4/3 to see that canceling. Okay. So this is going to be 4 to the third to the negative 4/3. These cancel, and I'm going to have 4 to the negative 4, which is 1 over 4 to the 4th, which is 1 over 256. How did I know that? Because 4 squared squared. 4 squared squared. That's 16 squared, which is 256. Okay, that was problem number 3. Problem number 4 looks like 2 times 10 to the 4th to the 3rd. Well, so here's the thing. This is multiplication. 2 times 10 to the 4th to the 3rd. I don't see a plus or a minus here, so I'm going to apply that exponent to each of these. 2 to the 3rd times 10 to raising a power to a power, you multiply. 2 to the 3rd is 8 times 10 to the 12th power. I have to apply that cubing here as well as here. This is not the variable x. This is like scientific notation. All right, that was problem 4 on station 13. What about 5? 5. Oh, this reminds me of that first station we did. We had x to the 4/3, y to the 2/3 over xy to the 1/3. Well, I don't see any pluses or minuses here, so the first thing I'm going to do is apply the exponent. x to the 4/3, y to the 2/3, over x to the 1/3, y to the 1/3. And look, the bases are the same, and I'm dividing. What do I do with those exponents? I subtract them. 4/3 minus 1/3 is 3/3, which is 1. Hey, look, I'm dividing, and the bases are the same. What can I do with the exponents? Why, that's right, I can subtract them. 2/3 minus 1/3 is 1/3. So there's my simplified answer for number 5. Okay, last station. Last station is, more radical stuff. Okay, station 14. Let's go. All right, so we've got number 1, 9x square root of 8x minus 3, 2x to the third. So I want to simplify each of these radicals first because I can't do the subtraction unless these have the same radicand, the same stuff under the radical. So 9x, this is 2 times 2 times 2 times x. I can take a 2 out. So I'm going to have 9 times 2 times x. And what's left over? 2x under the radical. Here, I have my minus 3 still, but I have 2 times x times x times x. And I can pull an x out. And so then I'm going to have minus 3x square root, and what's left over? A 2x. So it looks like this is what they have in common. 18 of these things minus 3 of these things gives me 15 of these things. And so there's my answer to number 1 on station 14. Number 1 on station 14. How about number 2? Okay, 2 says cube root of 16 over x to the 5th. All right, so I'm going to think about that as the cube root of 16 over the cube root of x to the 5th. Now I know that 16 is 2 times 2 times 2 times 2, and x to the 5th is x times x times x times x times x. This tells me I need a group of 3 to get one out, and so I'm left with 2 cube root of 2 over, I can take an x out, cube root of x squared. Okay, and minimally this is fine unless it says, when given the choice, rationalize the denominator. I gotta rationalize this denominator. So I've got 2 x's, I need one more, cube root of x, cube root of x. So this is gonna be the cube root of x to the third, which is just x. X times x, I'm gonna have an x squared on the bottom. Now on top, I've got this 2 on the outside, and then 2x under the radical. So I would much prefer to see this rationalized version because the directions said rationalize. If the directions hadn't said to rationalize, then I would have stopped here. Okay, but our directions did say rationalize, so I went further. Okay, problem 3. 3 over the cube root of 4. Why, look, there's some rationalizing to do. Now, I know that many of you are going to want to do the cube root of 4 times 4 so that you can have 3 4s. But the problem is when we do that, I get 3 cube root of 16 over 4. Some people get here and say, I'm all done. But no, you're not, because look here. So that's 3 cube root 2 times 2 times 2 times 2 over 4. Look, I can take out a 2. And so I'm going to have 3 times 2 cube root of 2 left over, all over 4. This cancels here, and I end up with 3 cube root of 2 over 2. That's my answer, and I'm not done here. I've marked that wrong because you haven't simplified enough. How could you avoid that trauma? Well, remember when you saw 1 4 and you needed 2 more? I didn't see 1 4. I saw 2 2's. So I need 1 more 2. Cube root of 2, cube root of 2. So now on top, I have 3 cube root of 2, and on the bottom, 2 times 2 times 2. Hey, that's the cube root of 3 2's. I get a 2 coming in. Same answer, less work, because I saw this as 2 2's, and so I only needed one more. Okay, problem number 4. Well, look, more rationalizing. 3 plus root 2, 3 minus root 2. So what is it that I'm supposed to rationalize with here? That's right, it's not just root 2, it's the conjugate, 3 plus root 2, 3 plus root 2. And I'm going to have to FOIL on top and FOIL on the bottom. On the bottom, because this is a difference of squares, the middle terms cancel out. So I just have this one squared minus this one squared. On top, though, I've got a FOIL. 3 times 3 is 9, plus 3 root 2, plus 3 root 2, and then root 2 times root 2 is the square root of 4, which is 2. Okay, so let's tidy this up. 9 plus 2 is 11, plus 6 root 2, all over 7. There's my answer to number 4. And finally, we've got some FOILing, plus root 5 times x minus root 5. This is a difference of squares, and I really would love it if you knew that a difference of squares is always going to be this one squared minus this one squared. But just in case, x squared minus x root 5 plus x root 5 minus root 5 times root 5 is 5. These are opposites, so they cancel, and we get x squared minus 5. Well, I hope this was helpful, and I hope that you're getting ready for our first assessment. I can't wait to see how you do. This will be, just like the graphing quiz, this assessment will really tell us whether or not you've been doing the online learning that you're supposed to be doing. Remember, you're supposed to be watching the videos. You're supposed to be taking notes from the videos. You're supposed to be asking questions on the Zoom. You're strongly encouraged to do every single homework assignment. Right. It takes a lot of discipline. You could very easily fail this class by staying on summer vacation. Please don't do that. Please. Join back in, reach out, ask questions, and you could still make a go of this. It's not too late.